All right.
What's up, guys?
Hey, Clayton.
Hey, Jesse.
If you work blue stuff, you like your second order will like you more.
You were blue stuff?
Oh,
Red stuff, you may play even like you know.
no introduction going on?
What about,
So what's the story with the color thing?
I was just asking, just to ask.
All right, that's fine.
Blue.
My daughter's is purple.
See it now.
That's just whatever. Actually, this is all based on whatever's available at the
Right,
store.
whatever it is.
Ah.
My entire wardrobe, almost my entire wardrobe is thrift store stuff. So why spend money on something that, you don't need to spend money?
Right.
All right. Oh, I'm going to put that thing on. Okay. See, there you go. Another one.
Oh. Not the 9680.
All right, that'll do.
That's better.
Okay, so today we're talking about strain. Last time we talked about stress. This time we're talking about strain. So just as stress normalizes load by considering the cross-sectional area of the member that's being loaded, similarly strain normalizes the deformation to that stress, the deformation that responds to that stress. So in other words, if I have a component and I apply a load to that component, I apply a load to that component will deform. Right? It'll stretch. So if the component starts off with an initial length L naught, there will be some increment of length delta that is the change in length, the extension, that is the deformation. Right? So we want to be able to characterize that deformation, delta. So on what does that delta depend? On what geometric features of the component does that delta depend?
Area.
So area is captured in stress, right? So in area, we converted this to a stress by compensating for the area. So now if I have doubled the area, I have to double the load to get the same stress, right? So the point is, if stress is fixed, because area is compensated for already in stress, then what other geometric features are going to change the strain? What's that?
Length.
So which is it, volume or length?
Length.
Right, so length. If I take a short piece of rubber band and I put a 1 pound mass on it, it'll pull this far. If I take a long piece of rubber band and put a 1 pound mass on it, it'll stretch more. Delta depends on how much length I had to begin with. Does that make sense? Okay. So delta is some function of L naught, right? That change in length depends on how much I started with. So what we do is we define strain using an epsilon as the ratio of delta to L naught, just like stress was the ratio of force to unit area. So that if I double the initial length, I'll get double the stress and still have the same strain. Just as if before, if I doubled the area and doubled the force, I would have the same stress. Okay. And that represents then the average strain. The instantaneous strain or the local strain is defined as the limit as L naught goes to 0 of delta over L naught. Right, the limit for some gauge length, it gets very small. But because delta and L naught are measured in the same units, strain is actually a unitless quantity. There's no units in strain. but we usually actually list strain as, let's say, I don't know, 325 times 10 to the minus 6. Okay, so that would be a value of strain, no units. But we'll oftentimes list it as inches per inch or meters per meter. So oftentimes you'll see strain with meaningless units. It's the ratio of the same units. Or you might see it as, in this case, 325 microns per meter. So they build the factor of 10 to the minus 6 into the units instead of building it into the actual value. Or you might see it listed as just 325 microstrain. So just if you put the micro in there and drop the meters out. Or finally, you might see it listed as 0.0325 %. So several different ways to represent the strain. Okay? We good with that? So that's normal strain, right? Because I've elongated it, I've applied a normal load. All of that, we have to get a new marker. Is normal strain. So now, instead of normal strain, there's another kind, we'll talk about another kind of strain. What do you think it's going to be?
Shear strain.
Shear strain, right? We have normal strain, with normal stress. You have a question?
I do. If you have a member and you are hanging something from, let's say, the center of the member, like a hole in the center of the member, and it's pulling it down so that it's deforming slightly, is that a combination of stress and strain, or is that just strain?
So the deformation is strain. The applied load is stress.
So the fact that it's going down means that it's under strain?
If there's any deformation, then the thing is strained.
Okay.
If there's any load applied, then there is stress.
So that would be both.
So there would be both stress and strain. The stress and strain go together. You always have the two together. You can't get a strain without a stress.
Okay, what if you took the load off of the beam and it was past the elastic state or whatever, and it,
We'll talk about that on Monday.
is that just strain?
So that's residual strain, but we'll
Okay.
talk about that on Monday. Yeah.
I got a question. This delta function, is this just the change in distance?
It's
or
not
is-
delta function, it's just delta, the symbol that your book uses.
Oh, okay. So is it a function of L naught or is it just like the change? in
Well, that
distance?
just, delta depends on L naught, right? So it's a function of L naught.
Oh, okay.
And the relationship between them is the strain, right? Delta equals strain times L naught. Right, so if I rearrange this equation, delta is a function of L naught, in that it is strain times L naught.
Okay.
Okay. So delta is just this distance.
Okay.
It's just a measured quantity. All right, so that's normal strain. Then we have shear strain. So shear strain is a response to shear stress, just like normal strain is a response to normal stress. So how do I, if I have the same block or some other block, how do I apply shear stress to it? Let's say I wanted to apply a shear stress in the horizontal direction to that chunk. What would it look like? It doesn't count unless you say it out loud.
Two forces in opposing directions on each side?
So you're saying this?
Yeah.
Right, so that would be a shear stress. Right, so shear stress is a stress on the top surface that's not orthogonal, that's in the plane of the top surface. And as a result, it will deform something like that. Right, does that make sense? We measure the amount of deformation, gamma, as the shear strain. Although sometimes it might be easier you measure that angle theta, I'll actually call it theta prime. It might be easier to physically measure that angle. See what I'm saying? Because you start with something that's a right angle, you know it's a right angle. When you end, you can't say, well, how much did it move? What you do is you measure the residual angle that's left, and then subtract it from the 90 degrees that was there to begin with. So in reality, we often do this as pi over 2 minus, well, theta prime, or pi over, for average. Okay. If we wanted, let's say that block has dimensions delta x and delta y. If we want the localized, instantaneous, if you will, shear strain, then we take the limit. So it's pi over 2 minus the limit as delta y goes to 0 of theta prime. So in other words, I have a chunk that has a shear strain on it. I want to find the local shear strain at a point. I have to take that chunk and shrink it down and see how small it gets. Find the, and actually technically delta x would also be going to 0. All right, you want to shrink this chunk down to a point. Does that make sense? So shear strain is just an angle. So shear strain has units, if you will, of radians, but radians are not really units. You guys know that, right? Okay, so it's effectively a unitless quantity, just like normal strain is. Whereas normal strain changes, Blake pointed out, this changes volume. Right, we're changing the volume. When we divide out the area, we get the volume. That's where we get the element from. This changes the volume. If I pull on the thing, I make the volume bigger. This shear strain changes shape. So a change in volume corresponds to a normal strain. A change in shape corresponds to a shear strain. Okay.
You can actually change the volume of the beam by pulling it.
Yeah.
It doesn't, the volume's not constant.
No. It depends. There are materials for which the volume is constant, but they're special material. I mean, they're a particular set of materials, very limited set of materials, for which that's the case. Most real materials you pull on it, and the volume changes.
Okay. Because like with Play-Doh or whatever, if you try to pull it apart,
It
it's
necks.
skinny in the middle.
Right. So necking is, again, we'll talk about that on Monday as well. Okay, we're trying to introduce things one at a time. But sorry. All right. So would you like to just skip to chapter, was it 14 that we're going to at the end? Go right into buckling? Actually, I think that's chapter 13. But anyway, okay. So in a most generic case, I'm going to try to draw this on the board. I was going to try to draw this ahead of time on an overhead, but I ran out of time. So let's say I start off with a block. I'm going to be really particular here to make sure I get this as square as I can. I start off with a block. And that block is sitting on the origin. So we have a z-axis, a y-axis, and an x-axis. And now what I'm going to do is I'm going to distort it. I'm going to grab hold of this end here and pull on it, this corner. If I grab hold of that corner and pull on it, I'm going to get something that's going to look like this. This is so hard to do. Okay. Oh, man. I'm pulling the fork corner from the back corner so that this is actually coming out towards you. That's why I said it makes it look, it's really hard to see in 3 dimensions, that's why I wanted to draw it ahead of time. On the overhead, because I'm
You're
not gonna be
pulling
able to
the
get
back
it.
corner this way.
I'm leaving the back corner of the origin, taking this corner and pulling it out this way.
Gotcha.
Okay. So I'm gonna draw it poorly, but I'll just try to fake it. So I'm gonna draw it, I'm just redraw it, that's what I'll do. I'll redraw. So I end up with something that looks like this. Something like that. Let's try that. Okay. I've tried to exaggerate it as much as possible. You see what I've got there? So I've taken this thing and I've pulled it all apart. So now I have a new, this is going to be my delta z, my new z or z prime. This is going to be my new x. And z, x, and y is going to be, oh no, that's my delta y. And then that's delta x. Everybody kind of see that? See what I'm talking about? Delta x, delta y, and delta z are the new dimensions in the x, y, and z direction. So I started off with values of x here, y here, and z here. Okay. Actually, let's not make it delta. Let's make the original ones delta. Apologize to those of you who are using pen. Never use pen in my room. Anybody using pen? Bold move, man. Bold move. Okay, let's call these delta. Delta
Always
z.
live left on the edge.
So we have z prime, the new z prime. Let's just write what it is. 1 plus epsilon in the z direction times delta z. And this is 1 plus epsilon in the y direction times delta y. And this one is 1 plus epsilon in the x direction times delta x. Okay, so we've strained them. There's the lengths of the sides in the x, y, and z directions have become longer. Right? The distance from the top plane to the bottom plane is greater here than it is here. So delta z is 1 plus the strain in the z direction, the normal strain, times what it was before. You see what I'm saying? Right, so delta, because this is the change over the initial length. So we've made each of the sides longer by pulling it apart. We could have made them smaller by squeezing it together, but in that case, epsilon would be negative, because delta would be negative, it would be shortening. Make sense?
So it's like a 3D normal strain.
So we have a 3D normal strain, plus we also have, yeah, I think I did it that way, okay. Theta prime x, theta prime z, and theta prime in the y direction. So those are the thetas, the angles, about the x, y, and z axes. Because theta prime x is not 90 degrees, we know that gamma about the x-axis is equal to pi over 2 minus theta prime about the x-axis. So this little angle in here, if I were to draw, that's gamma sub, gamma sub x, right? The strain, the shear strain at that little angle in there. But again, we typically measure theta prime x. If I have something, unless it's silly buddy, if I have a piece of steel or something, I pull on it, this is going to be, 89.995 degrees, right? It's going to be really small deviation from 90 degrees. So it's going to be really hard to measure gamma directly, but I can measure theta prime and then do the subtraction. Okay. And similarly, gamma y is equal to pi over 2 minus theta prime y, and gamma z is equal to pi over 2 minus theta prime z. And those are all, the angles are all defined, the shear strains are defined by the axis about which the strain occurs. So gamma x is about the x-axis. Make sense? Okay. Okay, so that defines shear strain and normal strain. Anybody have any questions about those before we jump in and solve some problems? Problems. No? Okay.
Wait, can you recall, you said gamma x is about the x-axis, so
So the x-axis in this picture, the x-axis is coming out of the board here, right? From the top picture. So that angle is measured about the x-axis. It's a rotation about the x-axis. Right, the line that was vertical is now over here. It's rotated about the x-axis.
And that's gamma with respect to z.
That's gamma with respect to x because it's about the x-axis. Gamma with respect to z would be this one up here because it's about the z-axis. Right? It's the
This way.
it's a right-hand rule again.
Right.
Put your fingers in the direction of the angle. Your thumb points in the labeled axis.
Okay. So, so you wouldn't have your delta x normal would be in the same plane as your, would not be in the same plane as your.
Right. So the delta x normal, the extension is in this direction, in what effectively is out of the board in this isometric view. But the rotation is about that axis. So you have motion, you stretch it here and you rotate it here. Right, so I stretch and I rotate. Those are the two x components.
So would all the gammas be in a singular plane?
Each of these gammas, in a Cartesian definition, yes, each of these gammas is in a particular plane.
Would they all be in the same plane? So would they be in the z,
No, they're
y?
different planes, right? Each one's a different face. This angle is measured on this face.
Oh, right.
That angle's on the top face and
That's
that angle's on the
question.
face. Okay. Everybody visualizing that okay? Okay. All right, so let's do the two problems that we've got up here. Start with 213. The piece of rubber, so it's a square piece of rubber, is originally rectangular and subjected to the deformation shown by the dashed lines. So this is a two-dimensional representation of the same thing. Determine the average normal strain along the diagonal DB and the side AB. Okay, so DB is the diagonal across the face, and the side AD is the one on the left-hand side that we can't see. You see what I'm saying? It comes up here. So the side AD is this side that we can't see, right? That's, if I were looking at the block, it would be the side facing this direction. Okay, and then the diagonal is that diagonal. Okay, so the object is to find the normal strain on each of those dimensions. So, everybody got the question? So then, how do we go about finding the normal strain in each of those?
It looks like the normal strain about dB would be negative.
Okay, first of all, well, we don't know. We've got to do the math and find out.
You can't just look at it and tell if it's squished in.
Well, you're relying on the fact that that's a accurate drawing, I mean, we don't, you know.
Okay.
Okay, it looks squished in, I see what you're saying, yes. But we don't know that it is. Okay. So how would we find what we're looking for? What do we need to know? Trying to find normal strain, what do we need to know?
We can find the points of corner ABC and ABC in space.
The original
Using- So we can find a like change in diagonal length.
So your points D and B.
Oh, yeah.
Right. Okay. Okay. So you're trying to find points D and B in space. Well, they gave us that information.
The
Right,
new
that's what the
points,
dimensions are shown there on the screen.
but the new points.
The new points are shown.
Yes, they are, yeah.
See the little, okay. So, what do I need to find? If I'm trying to find normal strain, what symbol am I trying to find? What symbol do I use to represent normal strain?
Look,
Epsilon, very good. Epsilon. I'm trying to find the average normal strain. How do I calculate the average normal strain?
change in length over the original.
All right, so we write it as delta L over L. Right, as in the book, they write it as delta over L naught, whichever way you want to look at it. The change in length over the length. Or, you could write it as L minus L naught divided by L naught. Right? That's actually going to be the most convenient way to work with this problem. So then we only have to find L for, which one are we doing first, dB? dB. And we have to find L naught for dB. So how do we find L and L naught? What's that? Pythagorean theorem? Well, that'll work for L naught, certainly, because it's a nice right angle. So, okay. Yeah, I meant L naught, even though L
Oh,
is
well,
first.
okay, my first step would have been to do the easy.
L naught first? Okay, that's fine. So what's the Pythagorean square,
L
square root?
naught's 500.
That's a 3, 4, 5 triangle, right? So then,
Busting that out.
since we're just skipping to the end, we'll just go ahead and put that in there, fine.
I mean, it is simple.
It is, it is.
I didn't know there was
So-
such a thing as a 3, 4, 5 that.
Seriously?
There's also 5, 12, 13 or
Okay.
something.
5, 12, 13 is another one, yeah.
But now I
That's
know.
my base of numbers.
Yeah, well, those are the ones they always use in physics problems, so you can quickly skip to the end on the MCAT. Anyway, or whatever test you're taking. So that's L naught, what's L final? How am I gonna find L final?
Isn't there an extended version of this? There's another version of it for right triangles?
Of the Pythagorean theorem?
No.
Yeah, but you need the angle in between them, which we don't have here.
Um,
Yes, law of cosines is the Pythagorean theorem applied to non-right angles.
Yeah.
But we don't have the angle in between them, so.
Gotcha.
How are we gonna find it? I mean, we can take an easy way, there's about 1,000 ways to find this, right?
I got a question.
Yeah?
Could you take 2 and 3 and turn it into its own right triangle and then subtract the hypotenuse from 2 and 3 to 500 to find the, or that would, or I guess that would be the change. Is that possible?
Okay. It's probably a little exaggerated, but there you have it, right? So I still can do the Pythagorean theorem. the horizontal distance from here to here, right, I can make a right angle out of this. It's in 2 dimensions, it's easy enough to do that. Now, if it were in 3 dimensions, I'd probably do vector subtraction. Right, I'd subtract the coordinates. But if I, j, and k for this position and I, j, and k for that position, and do a subtraction. Because it's just easier once you get into 3 dimensions than trying to map out a right triangle. You know. But anyway, this is the easier way to go. So now I've moved in by 3 meters, so this one is 297. So I moved in 3 millimeters on that side. And this side is 398, because I moved 2 millimeters up. So we get
496.6.
496.6, and probably you want to go one more, but it's 0. So you want to go at least 2 sig figs beyond what you're, beyond the 3 that the system is going to ask before you come. Okay. All right, so then I just have to go back and plug in. So L is 496.6 minus 500 divided by 500 equals negative 0.00680. Somebody else get the same thing? Yeah. Or 0.68, negative 0.680% strain. And it's, did you get the value you wanted, Colin? For, what'd you say about dB? It should be what?
Negative.
Negative. So we got negative value, so we're all good. Okay. Okay, so how are we going to do AD, side AD? What do you want me to write down? What do you want me to write down? Find the strain side AD.
So we find gamma?
No, we're still looking for normal strain.
It's
Just a different size.
Same process, you just use the Pythagorean theorem of 400 millimeters and 3 millimeters. 400 squared plus 3 squared. Agree with that? That'll give you the new L. And then L mass just 400.
Everybody see that? I'm trying to find the normal strain inside AD. Side AD is elongated, right? Because it's now the hypotenuse instead of the long leg with that little skinny triangle. Good? Okay. And if you do that, I think you get 2.81 times 10 to the minus 5. Yep, okay. Or we might list that as 28.1 microstrain. Good?
And then now we're trying to 100%. Because now we're moving on to, I guess we don't.
So we're moving on to 227. So
We're moving on to the next problem.
Yeah. The next problem is where we're going to ask about shear strain, right? Okay? Supposed to be excited, this is. At least you're awake, I give you credit for that.
For some reason on that last part, I was thinking that, I don't know what I was thinking. I was thinking that AB is supposed to be a diagonal as well, and I was really confused as why it was labeled as a diagonal. And then I was like, oh, maybe there's like another face back there, and B is like the back corner, A is the front corner,
No,
and then.
it says side 80, it doesn't say diagonal 80.
I know. That's why it confused me with the 400 and the 3, and then I looked at it and I was like, oh, just the,
There you go.
just that side.
Okay, so everybody got 213. Okay, let's move on to 227. Somebody throw something at Clayton, we're gonna make sure he's getting away. All right. We need to bring in the water squirt gun. I think I'm gonna enable cables in the squirt gun.
Ooh. Actually, I have the perfect thing. My mom got me, it's like this.
Super soaker.
No, it's like this thing, it's like a tub, and it has like one of the things on it, but it's bigger, and it comes with water balloons in it. So you just put the water balloon on the squirty part, and you just like fill up your water balloon.
Really? I don't think we want to go as far as a water balloon.
You can hold it.
But I could just, instead of filling it with water balloon, just squirt it across.
All right, 227, square plate.
Huh?
ABCD is deformed into the shape shown by the dashed lines. And DC, well, here, let's draw it. We start off with a shape that looks like this. And, oh, it's a square. And then it's deformed into a shape that looks something like this. Right. So we have A, B, C, D, and A prime, B prime, C prime, and then D doesn't move. Okay, if DC has a normal strain, so the normal strain on DC is 0.004, and DA has a normal strain of 0.005, and at D, gamma, well, in this case they've labeled it gamma XY, because it's gamma about the z-axis, but it's on the x-plane in the y direction. It's the result of, did they label gamma XY in there anywhere? No, they didn't. Oh, interesting. So gamma XY is equal to 0.02 radians. How much? What's that?
You get that from like the A to the A, like AB to A prime D.
I'm not sure. What'd you say?
Where is that in the picture?
That's what I'm saying. They didn't label the gamma. It's the angle. It's this angle.
Okay, so I'm between AB and A prime.
Right. So between AD and A prime D, I get you, right, yes, between those lines. So determine the shear strain at point E, so we're supposed to find the shear strain at point E with respect to the X prime and Y prime axis. Okay, so does everybody understand? Here, point E's in the center. So everybody understand what they mean? So the X prime and Y prime axes essentially 45 degrees from the base axis, x and y axis.
Does it want us to find? Wait, can you label where that strain would be?
Where that strain would be. So if you, what is that? Interesting. Oh, the drawing's not very good. That's gamma E.
But since it says X and Y. do
What's
we
that?
need to do it- But since it says X and Y, do we need to do it for that one and the one that does the other coding?
No, because
Or we just-
the difference between them is rotation. So the strain, and remember I said before, the stress in the x, or stress, the shear stress in the xy is the same as the shear stress in the yx.
Mhm.
So the shear strain in the xy is the same as the shear strain in the yx.
Okay.
Okay. The only difference, if they're different in a particular orientation, is because there's a factor of, there's a rotation involved.
Okay.
Okay. All right, so, I think that's all we have to do. Okay, so where do you want to start? Really? Come on. I'm guessing that comment had nothing to do with the problem 2.27.
No,
Okay.
Blake got me off topic. That's actually
Ooh.
complete lie. I was just kidding.
I suspect that perhaps we're going to have to break this little group up over here later in the semester, so. If you can't maintain your focus, boys, I'll separate you. All right, seriously. So, where do we go? We gotta find that angle effectively. How am I gonna find that angle? We're all just gonna stare. Nobody has any ideas where we might start? Just, let's pick something.
I'm curious about
Figure
gamma XY.
Can we find,
Okay, well, first of all, let's answer curiosity. Gamma X, what is it?
Where is it? where's gamma X,
That's
Y?
what Kayla asked earlier. It's
ADA prime.
It's between AD and A prime D.
Okay.
It's that angle in there. So what do you think we're gonna need to find here?
the first thing I would do is probably solve for the new links.
So what's that?
Solve for the new links of A prime,
So A prime D, for instance?
yeah, and then like C prime. Or what,
Okay.
yeah, D.
Okay, let's start with that. Let's find, I'll start with our lengths. So, what is the, which one do you want to start with? Do C prime D? So what is the length of C prime D? How do I find the length of C prime D?
You do the, minus, with the L, the new one minus the original one.
Okay, but I'm not trying to find the strain, I'm trying to find the length.
Multiply the strain by the initial length
Multiply the strain
by DC. So 600
times
millimeters.
length of DC at the beginning. Is that what you want?
Um,
Are we okay with that? What strain?
Delta
which strain? I was given two strains.
Oh. That strain of DC.
Okay, strain DC. Okay. Everybody happy with that? Right, you have to multiply it by 1 plus strain. If I want to find the delta length, then I